So, next is we will come to another two things, that is that shunt capacitors and series capacitors, right. So, shunt capacitors basically used for a lagging power factor circuit. When you have solved that circuit theory problem, AC circuit theory problem, you might have solved the problem when capacitor is connected across the load to improve the power factor, right. So, the effect is to supply the your requisite reactive power. So, shunt capacitor basically it injects reactive power. Now, capacitors basically you will find shunt capacitors generally connected to a bus bar. If you go to any substation, there you will see the shunt capacitors are there. If you go to any substation 33 kV or above, then you can see it, right. And disposed along the route to minimize the losses and voltage drop. Basically, shunt capacitors actually, right. I mean, first telling one or two line, when it is connected in the transmission or distribution system, the primary objective of the shunt capacitor is to reduce the power loss, right, and though not much, it improves the voltage magnitude also. And in the case of series capacitor, just reverse. Series capacitor's primary objective is to improve the voltage magnitude, and though not much, it reduces the power losses, because power loss is inversely proportional to the square of the voltage magnitude. So, as the series capacitor improves the voltage magnitude, so to some extent it reduces the power losses, but basically primary objective of series capacitor is that it actually improves the voltage magnitude, whereas a shunt capacitor, the main objective is, the primary objective is to reduce the power loss, and though not much, it improves the voltage magnitude. These two should be in your mind, right. So, capacitor is basically is a constant impedance type load. Later we will see, I will try to show you here that impedance constant impedance type load, right, and that value, the reactive power which it injects, actually it is proportional to the square of the voltage magnitude at where it is connected, right. Therefore, when voltage is suppose capacitor is connected at a 33 kV bus bar, right. So, whenever you are buying capacitor from the manufacturer, suppose its rating is say 5 megavar for example, that is actually specified at this 33 kV voltage level, right. That means, when voltage level is 33 kV, it will inject 5 megavar. Generally, you will find that at 33 kV bus bar, voltage may not be 33 kV, it may be 32, 31 or 30 kV, right. But capacitor, that reactive power injection actually is proportional to the square of the voltage magnitude. If 5 megavar it gives at 33 kV, then suppose voltage instead of 33 is 30 kV, that means reactive power injection will be 30 upon 33 whole square into 5 megavar. That means, it will not inject 5 megavar, rather it will inject less megavar into the network, right. So, that is why as the voltage falls, the bars produced by a shunt capacitor falls, thus when needed most, their effectiveness actually falls, right. Anyway, so that is that your what you call shunt capacitor. Now, take a simple circuit, right, with and without shunt capacitor. So, this is the circuit, this is that simple series circuit, say, right, and R and X value, this is sending and voltage receiving. One thing I could like to tell you, whenever we take Vs, Vr, all these things, it is all per phase voltage, Vs, Vr, all per phase voltage, line to neutral voltages, right. So, this is R and resistance and your reactance of the line, inductive reactance of the line, and if you draw the phasor diagram same as before, this voltage is your Vr, this is Vr, right, and this is your IR. Magnitude, understandable, it is everywhere it is magnitude, I am not saying here, this is the IR drop, this is IXL drop, and this is this dash green line is IZ, and this is Vs, this is the your without capacitor, and figure A and figure C, actually this is the phasor diagram without shunt capacitor. Now, in figure B, a shunt capacitor is connected, right, at the receiving end. So, in this case, because of that IC is the leading current, this is your, this voltage is Vr, this voltage is VR. So, leading current IC leads actually VR by 90 degree. So, this is the leading current. Now, this current initially this without capacitor this current was I. So, here it is I, but this leading current is there, right. So, that means this IC is made it upwards, and then this is the resultant current I dash, right. That means this is the I dash. Initially it was I, now due to capacitor the current is I dash, that means current actually is decreasing because of this, right. So, this angle is theta dash, here is theta, here is theta dash, here is delta, it is delta dash, and that means this current is I dash now with capacitor. So, this is I dash R, right, this is I dash XL, right, and this is I dash Z, this green line, and this voltage your what you call that your Vs, right. So, that is your, that means what, that capacitor actually that as soon as you put it, that capacitor actually it's your reduces the current, because it here it was I, now it is I dash. So, it is magnitude is reduced and changing the angle also. Now, in this case, if you if you see that delta and theta, here it is delta dash theta dash. So, later we will see because of this changing delta dash or theta dash from delta and theta, it improves the power factor of the load also, right. Now, as I told you that capacitor actually it injects your what you call reactive power. If you look into this this diagram, I will just show you this way. For example, this diagram, right. Now, this is that Xc is the magnitude, that is reactance, right, 1 upon omega c, right. So, as capacitor is constant impedance type of load, because Xc is equal to 1 upon omega c, we assume that omega is equal to this thing, omega is not changing, because if we assume 50 Hz 60 Hz system, generally F remains more or less constant. So, reactance remain constant. Now, question is that take this simple circuit, right. Now, I will take only the magnitude. So, this current magnitude IC actually it is VR upon XC, right. This is the current magnitude. Therefore, my here also IC magnitude, right. That means IC square is equal to XC square, right. Now, reactive power QC is equal to actually IC square into XC, that is actually your this IC square actually VR square into XC by XC square. That means, QC, that reactive power comes from this, is equal to VR square XC, right. That means that this is that VR square upon XC, that is the reactive power supplied from the shunt capacitor. Now, if we assume that VR is constant, for example, right, then and XC also frequency will remain more or less constant, right, omega XC is equal to 1 upon 2 omega c, right. So, that is your it is omega c into VR square, and that is equal to 2 pi f, right, into c, then VR square. This f frequency remains more or less constant, right, and if for a nominal voltage, if we assume VR is constant, so naturally capacitor is a constant impedance type of load, because frequency is not changing, right. Second thing is, as I said, capacitor that QC injected is proportional to the voltage square. Just now we saw this thing, say QC is equal to your VR square upon XC. Generally what happen in the case of when you buy from manufacturer, it is actually nominal thing is that QC nominal value, right, is equal to VR, nominal means rated, right. So, VR that is nominal, right, square upon XC. This is that your what you call this, but if it is not, then this is say equation 1, right, and if it is QC is injected at any voltage VR square say upon XC, this is equation 2, right. So, this is actually QC nominal and this is actually QC you are getting at any voltage VR, right. That means, if you divide that is equation 2 divided by equation 1, then you will get QC by QC nominal is equal to, you will get VR square upon XC into XC divided by just hold on, divided by your VR, right, then nominal square. XC will be cancelled. That means, here I am writing this thing as a phrase, that means QC is equal to QC nominal, right, into your magnitude of your VR divided by magnitude of VR nominal, right, whole square. That means that if magnitude of VR is equal to magnitude of VR nominal, then QC is equal to QC nominal, right. But if VR is less than this thing, for example, suppose QC is equal to QC nominal, say 5 megavar, say magnitude of VR is equal to 33 kV, say, right, and magnitude of VR nominal is equal to 33 kV, say. That means, QC is equal to 5 into your 30 by 33 whole square, right. That means, 5 into your 100 by 121 megavar, right. So, that means what? That only at rated voltage this 5 megavar will be injected into the network. If it is less than that, then your voltage, this QC will be 5 into 100 by 121, right. So, roughly it will be your nearly 80%, say. I do not have calculator to calculate. So, that means slightly more than perhaps 4 megavar will be injected, right. That means, whenever it is needed actually at that time, because when voltage is low, at that time it injects less, your what you call less megavar, right. So, that is this thing. That means QC, that capacitor thing, it is proportional to the your what you call voltage magnitude square, and second thing is capacitor actually is a constant impedance load, right. So, this is your, hope these things are understandable to you, right. Later we will see, when we will take the transmission line also, at that time we will take some problem, at that time things will be, but one thing I am telling, this VS, VR, whenever you will solve, everything should be on per phase basis, right, and this power factor improvement. Next is that series capacitor. Series capacitor actually it is connected in series with the transmission line, such that inductive reactance will be compensated by the your capacitive reactance, but those things are not discussable in this course, but resonance is another problem for series capacitor, but we will not discuss on that, right. So, one major drawback of the series capacitor of course is the high over voltage produced, right, when a short circuit current flows through it, right, and special protective devices need to be incorporated, such that spark gaps and nonlinear resistor. These two also will not discuss here. If time permits at the end, then something new I will try to tell, but right now we will not go through that, right. So, series capacitors you need, when you are connecting series capacitor in a line, you need lot of your what you call protection, right. You have to be very careful, right. So, figure we will take a simple your what you call simple circuit diagram for that series capacitor. Suppose you have a transmission line, this sending end voltage, this receiving end voltage, this R and XL is the transmission line, a series capacitor is connected in series, right. So, just I will give you one I will tell you one thing, you find out what is the reason. Generally series capacitor they give, it is analogous to voltage regulator, right. So, why that you find it out, right. So, series capacitor, this thing is in series with that your what you call in the line. So, that means impedance Z dash, actually when capacitor was not there, Z is equal to R plus Jx, now it will be R plus J XL minus Xc, and this is the thing. So, what will happen that because of this Xc, this XL minus Xc component will reduce, naturally voltage drop will reduce. So, hence the receiving voltage will be better, it will be improved voltage, right. Now, if you draw the diagram instead of separate diagram like shunt capacitor, we had 4 diagrams, 2 phasor diagram, 2 circuit diagrams, here only one we have made it. So, this is the current flowing through this I. So, this is the current, I is angle theta say, and this is the receiving end voltage VR, and again and again I am not putting IR, that I magnitude, but understandable, right. So, this part, this is theta, this part is IR, right, because it is I is here. So, this IR drop and 90 degree with this black one, it is actually IXL, right. I am not putting magnitude again, but understandable IXL. Now, this XC is also there, because it will be minus IXC. So, that is why this red one arrow is downwards, because subtraction, right. So, it is I into XC. So, resultant actually I into XL minus XC, that is this part I into XL minus XC, and this is that your what you call that Z dash into your I, right. This dash line not written here, but this dash line is this thing. So, this is the sending end voltage and this is VR IR. So, this is the resultant phasor diagram. So, this part is IR cos phi and this side is I into XL minus X sin phi. So, automatically you can find out what is the relationship Vs VR on this thing, but this phasor together, this phasor diagram is shown, right. So, series now, so this is understandable, this is simple thing, right, very simple thing. So, only thing is that you have to see that this IXL, this IXC, because it is, if you multiply by I, then this is IXC. So, naturally this much will be reduced. So, this is the resultant, right. If the series capacitor is not there, then VST will go to the top here only, not shown, but here only, right. So, next this merits and demerits of using series and shunt capacitor, right. So, the relative merits between shunt and series capacitors may be summarized as follows, right. So, I have written few points, but I will tell you something also. So, if the load var requirement is small, series capacitors are of little use, right, because no need actually, if load var requirement is very small. Now, if voltage drop is a limiting factor, series capacitors are very effective, because it is actually reduce the voltage drop XL minus XC. So, series capacitor actually it improves the voltage, right. With series capacitor, reductional line current is small, right. Hence when you connect the series capacitor, it is XL minus XC, but ultimately it is R plus J XL minus XC. Just you have to, when you connect series capacitor, you have to consider many other design problems, I mean design parameters, just like that resonance is one, right. So, that XL minus XC component you cannot make it 0, right. So, XL minus XC component, right, that will be reduced, but in that case, but R is there, R plus J XL minus XC, remember, right. So, reduction in line current is small, although current will be reduced is small. Hence, if the thermal consideration limit the current, little advantage is obtained and shunt compensation should be used, right. Thermal consideration means that every transmission conductors has the maximum your what you call maximum current carrying capability, right. So, different conductors have different rating, they call thermal limit. Now, shunt capacitors improves the power factor of the load, it is true, whereas series capacitor has little effect on power factor. I told you the primary objective of shunt capacitor is to reduce the loss and improve the voltage magnitude, right. So, whereas the series capacitor has little effect on the power factor, right. For the transmission line where the total reactance is high, series capacitors are effective for improvement of the stability. For a transmission system, if a long transmission line, series capacitor will be very effective, right, and it improves the stability. Detailed studies are there for the higher level course, right, but for this course this is a general idea you have that between the series and shunt capacitors. So, if you have any questions or anything, when you will study this, you can send us a mail, right. So, but many other things are there on series and shunt capacitors, but that will take I mean long time, and it is beyond the scope for this course, right. So, up to this, that per unit your what you call power system component, per unit system, and booster transformer, regulating transformers, and series capacitors, shunt capacitors we have discussed, right. Next we will go to the characteristic or of the transmission line, that performance of the transmission line for short line, medium line, and long line, right. After that we will see voltage waves and other things, right. So, let us start with after this that short line thing, right. Just 1 minute, one few seconds, just wait, right. So, for this, for the characteristics and transmission line, right. So, this is another new topic for you, right. So, whatever phasor diagram we have made in the previous cases, here also will come, and those equations will come, right. So, generally for the transmission line, that it is convenient to represent a transmission line by the two port network, you know, right, wherein steady sending end and the sending end voltage V s and the current I s can be related to the receiving end voltage V r and the current I r, right, through A B C D parameters, right. So, generally this is generally you know that this V s we can write A V r plus B I r, basically its unit should be volts. So, I am writing here it is volts, and I s is equal to C V r plus D I r, this is ampere. So, this is a new topic started. So, this equation is 1 and this equation is 2, right. So, or in matrix form we can write V s I s this side is equal to A B C D V r I r, this is equation 3, right. So, A B C D parameters are that depend on the transmission line constant, right, your R, then your L, C and G. Of course, conductance will be neglected for our study, right. So, basically A B C D parameters, they all are complex number, right, and from this equation you can make out the unit, right, unit of all these parameters. For example, A and D are dimensionless, right, B is ohm and C is Siemens or mho, right. I will use for numerical other thing mho, right. So, and another identity holds for this kind of system, that A D minus B C is equal to 1, this holds, right. So, to avoid the confusion between total series impedance and series impedance per unit length, we will follow certain notation, right. So, notation means that we will follow this kind of notations such that right from the beginning I should clear everything, there should not be any confusion when we will derive this. For example, small z is equal to gamma plus your j omega L ohm per meter, right. So, it is actually series impedance per unit length, we are writing gamma plus j omega L. Then similarly, shunt admittance we will write is equal to G plus j omega c, it is Siemens per meter, I will use mho per meter, right. It is shunt admittance per unit length, and when small z small y, it is basically that parameters actually per unit length, right, per meter say, and capital Z is equal to small z into L, that is ohm, total series impedance. Similarly, Y is that total shunt admittance, small y into L, Siemens, I will use mho, some book they are using Siemens, that is writing S, or mho, MHO, right. So, total shunt admittance, and L is the line length in meter, right. So, these notations will be used throughout this. So, there should not be any sort of confusion, right. So, G will neglect it, as we have discussed earlier also, right. So, we will not talk about this thing. Next we will come for short transmission line. So, what we will say that capacitance, that is that your shunt capacitance may be ignored without much error if the overhead lines are less than 80 kilometer long. So, this 80 kilometer long or 60 kilometer long, these are some your terminology, right. We use 60, 80, actually it depends also on the your what you call that voltage level, right. So, or if the voltage is not over your, in our country it is 66 kV level is also there, 33, 66, 132, 220 and above, right. So, in that case we can ignore shunt capacitance, but for underground cable you cannot ignore, right. Underground cable you have you cannot ignore that those things, you have to consider the your charging capacitance or shunt admittance, right. So, so we will assume that line is less than 80 kilometer long, or if the voltage is not over 66. Ultimately it is not 80 or 60, you have to see that up to which length that charging admittance is not affecting that your performance evaluation of the transmission line, that is the major thing, right. So, that is why I have written it is not over 66 kV. The short line model on a per phase basis, that is why I have written here everything we will do on per phase basis, right, is shown in figure 1. This diagram we have shown earlier also, but at that time load was not shown. So, this is a short transmission line. So, sending in it is a nothing is there, no shunt connection, parallel connection, nothing is there. So, Is is equal to IR. So, sending in current is equal to receiving in current. Line impedance is R plus Jx, right, reactant impedance, and this is that receiving end load is connected and voltage across the load is receiving end voltage is Vr, right. So, this is a short line model. Now, if you write down this equation, so Vs is equal to Vr plus Zir and Is is equal to Ir. This is I mean if you apply KVL here, if you apply KVL here, so you will get this equation Vs is equal to your what you call this Vr plus your Ir into Z, right. So, this equation you will get. So, this is Vs Is is equal to Vr plus Z, although Ir and Is both are same here, this thing, right. Another thing is 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 equal to Ir. So, this equation is 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 equal to Ir, 0 into Vr plus 1 into Ir, right. So, this sending end and receiving end, this is A, B, C, D parameter, this is A is equal to 1 in this case, B is equal to, of course, here A is a real quantity for this one, right. Z of course is complex, C is 0 and D is 1. So, AD minus BC is 1, because 1 into 1 minus 0 into Z. So, that identity holds, and this is equation 4, right. The phasor diagram for the short line I will show you in this figure, right. So, we have also seen this one. So, this is actually voltage Vr, Vr is taken as a reference, right. What I will do, I will give you another thing, that instead of taking Vr as a reference, it is your job, you will do it, you take I as a reference and draw this whole phasor diagram. This is your exercise, right. Now, we come to this. So, this is Vr as a reference. So, this is IR, I have taken magnitude here, this is Ix and this is the voltage Vs, right. So, angle your that angle that between this I and the Vr is delta R, this green color, this is delta R, angle between your I and Vr, right, and angle between Vs and I is delta S, right. So, this red color delta S, and angle between Vr and Vs it is delta S minus delta R. So, this is delta S minus delta R, this is the angle between this Vs and Vr, right. And now, here EA is equal to IR cos delta R, because this is delta R, this is also delta R, right, and AB is equal to CD, AB is equal to CD is equal to Ix sin delta R, this is AB is equal to Ix sin delta R, and your EA is equal to IR cos delta. This we have seen earlier also, just now I have just in the previous thing we have shown, right. So, this is the phasor diagram, and magnitude I is equal to magnitude receiving end current is equal to magnitude sending end current. Now, from this only we can write magnitude Vs cosine delta S minus delta R, the projection on this is equal to your IR, look, these are magnitude understandable. So, every time I am not calling as magnitude, I will call IR understandable, right. So, IR cos delta R plus Ix sin delta R plus Vr, this is equation 5, right. Now, delta S minus delta R is very small, the angle between Vs and V are actually very small, we can take cosine delta S minus delta R approximately 1, that is delta S minus delta R approximately 0. So, cosine of this one delta S minus delta R approximately 1. So, here you put 1, then you will get magnitude Vs is equal to magnitude Vr plus I r cosine delta R plus x sine delta R, right. So, equation, this is equation 6. Equation 6 is quite accurate for the normal range of load, right. That means, because this is an approximation, delta S minus delta is an approximation, right. So, if difference is more, then we cannot make this approximation, right, but for nominal load this equation is more or less quite accurate, right. So, one thing I am telling, another exercise you try, that take I as a reference and redraw the whole phasor diagram for this thing, right, and see how it looks like. You will find perhaps rather than this one, that one may be easier to you, right, but I have not made it for you, you should do it. So, thank you.